for this kuliah. So I have been meaning to have this online lecture for a while. So the first person that I thought to work with definitely Dr. JP, because I had visited UNNES, if I'm not mistaken, last, and all teaching and learning need to be conducted online. So these online classes have started like for the past 4 to 5 weeks. So organometallic chemistry, actually the subject that I currently teach, I have around 75 students registered for this course, but not all of them are here because some of them might be having some connection problem. I did have connection problem just now, 10 minutes before this class started. So yeah, pardon me if I got stammered or if some of the connection lost in any way. Just alert me on the chat. So if you have any questions later, please drop your comments on the chat. So I will respond to the questions later at the end of the lecture. So thank you very much, UNNES, for having this kind of session. So in the coming weeks, probably in June, we're gonna have Dr. JP to give a talk on a few topics to my students, inshallah. Okay, so the topic that I choose to give today is organometallic chemistry, principle, synthesis, and application. So previously the subject was taught by Prof. Hada. Prof. Hada was one of the visiting professors in UNNES for the last 2 years. So for this subject, this is 2 credit hour subject. The code is CHM 676. This subject is offered to final year students. They are currently in their final semester. So I would like to start with the definition. I'm sure based on my discussion with Dr. JP, I was told that UNNES is offering about the same kind of subject. You also have your inorganic chemistry courses, am I right? So organometallic chemistry is not alien to you, I'm sure. So this is not totally new, but there will be few refinement that I would like to make here, especially on the definition. So we can have inorganic compounds, but not all inorganic compounds are organometallic compounds. So the best way to define organometallic compounds would be ones that have M to C bond. So M is actually metal and C is carbon. So for a compound to be classified as organometallic compound, it must have this metal to carbon bond. So we cannot say that as long as we have metal and organic compound in any given complex, we cannot simply say it is organometallic, not until we see that there is a obvious bond between metal and also carbon. And of course, some other compounds that do not have any M to C bonds can be said to be related to organometallic compounds, but they are not organometallic compounds. You might be saying like oxygen, sulfur, nitrogen, or phosphorus directly bonded to metal in metal complexes, but they cannot be classified as organometallic. So for the start, it is best for us to understand that for the compound to be classified as organometallic compound, it must be consisting of at least one metal to carbon bond. So other than transition metals, the organic compounds can also be complex with some other metals from the main blocks. And that's why we can have like boron, silicon, germanium, and so on and so forth. Okay, this is an important subject. This subject was introduced like 15 or 16 years back by Prof. Hada, and we would like to offer the subject to the students because approximately at least half of the world's research publications, chemistry, are related to organometallic compounds. So maybe the definition of organometallic compounds in the research article is quite broad, as in ada setengahnya yang mungkin melibatkan compounds yang tidak ada M2C bond, tetapi they are still considered as organometallic compounds, like cisplatin, oxaloplatin, so on and so forth. But they are still considered as organometallic compounds in the research article. But as far as the syllabus is concerned, we are going to focus more on M2C bond related compounds. So when we browse through the literature, we could see that half of the world's research publications mainly focused on the organometallic compounds. So that is how important it is nowadays. And second, because 10 of the world's top 30 chemicals that are being produced using organometallics as the catalyst. The simplest example would be maybe hydrogenation in the process of making margarine. These are important chemical processes where organometallic are used as catalysts. So it is important for us to know the chemical structure of the organometallic compounds, as well as how do we characterize it. So based on the title given just now, this particular lecture will be divided into few important parts. The first part will be this definition, which I consider as the principle of organometallic. And then the second part will be how are we going to synthesize the compounds. And then last but not least, a little bit on the application. So moving on, well, actually for this syllabus, since we can have many types of ligands. If you have taken inorganic chemistry courses, I'm sure all of you have understood the terms like ligands, nuclearity, then TCT, and so on and so forth. But since this is 2 credit hours subject, we narrow down the area of a scope, the scope of the subject, by focusing more on the carbonyl complexes. So carbonyl complexes, the ligand used here is carbon monoxide. The Lewis structure is given there. So we use carbon monoxide. This is called pi-acid ligand. I'm going to be explaining in further details later why do we call it pi-acid ligand. But as for now, it is best for us to accept that CO or carbon monoxide is a good ligand where it can be complex with various types of metal. So if we look at this, well, actually, this is just a revision from an organic chemistry course that my students have taken earlier in their 4th or 5th semester, when mistaken. But it is good for us to revisit these molecular orbitals. So we have, I just want to show this because later in our discussion, we are going to be using this quite a lot, especially the term like HOMO and also LUMO. So HOMO stands for definitely highest occupied molecular orbital. So for the molecular orbitals of carbon monoxide, it's going to be sigma antibonding. And LUMO stands for lowest unoccupied molecular orbital. And in this case, the LUMO is pi antibonding. So we are going to see some movement of electrons in and out from ligand to metal, metal to ligand, just to make in order to form the metal complexes. So let's see just a quick the bonding. Sigma 1 we have non-bonding. So because oxygen and carbon, they are having different energy. So the first orbital of oxygen does not involve any formation of the molecules. The formation of molecular orbitals or the overlapping of orbitals started from 2s of carbon and 2p our you can have a look here that the bonding started from sigma 2 and pi 1. So overlapping between S and P, overlapping between Py and also Pz. Just a glimpse through. So this is carbon molecule, carbon monoxide molecule. So we use this ligand to complex with various types of transition metals later. So we are going to use this ligand as our reference. Of course, in the real world, we can have more than carbon monoxide. Like in our research group, like Dr. Karima, me, and Prof. Hada, and Dr. Amalina, we are doing some other ligands which could be seen a little bit more complex than this. Like we have shift bases and thiosemicarbazone and thiourea and so on and so forth. But as far as for this syllabus is concerned, we're going to focus on carbon monoxide, and we're going to see how these complexes are formed. So it is good for us to understand now that for the molecular orbitals of carbon monoxide, we have HOMO, is occupied here, and we have also have LUMO here. Is that okay now? Am I going too fast? No, okay. Because I tend to speak very fast, so you need to stop me when you feel necessary. Yes. Okay. Composition mechanism. So this is how our carbonyl complexes are formed. So there are two steps needed to be taken in order for us to form one carbonyl complex. So M represents metal, and this is our carbon monoxide. So the first step is actually the field sigma orbital on the carbon. Well, actually, this is our HOMO just now. The electrons move from the HOMO of carbon monoxide into the empty orbitals of the metal. So I denote this as positive because metal is electropositive by nature, so it tends to be positive. And then there will be an overlapping of orbital between carbon from carbon monoxide and empty orbitals from the metal. So that's the first step, where there is the donation of electrons from carbon monoxide to the metal. And the second step would be the filled metal orbitals, because just now it was empty, now it is filled. This filled d orbital or hybrid molecular orbitals of the metal overlaps with the empty pi orbital. So this is our LUMO. So we are taking electrons from HOMO of carbon monoxide, and we are giving back the electrons from metal to the carbon monoxide, and that electrons will be transferred into our LUMO, which is pi orbital. So this is the basic or fundamental knowledge that we have to have in order to understand later the bond strength, the bond length, bond order, and also how do we characterize our organometallic compounds, especially using FTIR. So as I promised earlier, we call this pi electron acceptor. We call this pi acid ligand because they are pi electron acceptor. So this acid-base definition is actually based on Lewis definition. So Lewis acid is pi electron acceptor, and Lewis base pi electron donor. So in this case, we can understand that your ligand is acting, behaving as a pi acid ligand, pi acid, and then the metal is behaving as electron donor. So it is Lewis acid-base interaction between metal and also the ligand. So we are done on the first part of the lecture, which is on the principle, the basic principle, the basic definition, the introduction of organometallic compounds. We have talked about how to define. It should be compounds, complexes containing at least one metal to carbon direct bond. And we have also seen how carbonyl molecular orbital is constructed. That is the fundamental knowledge that we need to have in order to understand the formation of complexes. The formation of complexes consists of two main steps: the donation of electrons from carbon monoxide, and also the back donation of the electrons from metal, field orbital of metal, to our carbon monoxide. Now moving on the second part of this lecture, on the synthesis of carbonyl complexes. Now the methods that I'm going to be giving soon, this is based on the book, but definitely when you browse through the research articles online, there will be various ways of synthesizing our carbonyl complexes. And in fact, to synthesize organometallic compounds, we can choose so many methods. So from conventional up to the recent one. Now the first one is direct insertion of metal with carbon monoxide. Only iron and nickel can do this. If you try with something else, like vanadium or scandium, you'll be a little bit tricky and tedious. You might not be getting your carbonyl complexes. But the thing with this compound is that they are very toxic. Direct insertion meaning we are just passing through your carbon monoxide with the metal, and you're going to get your organometallic compound. So we have iron pentacarbonyl here, and we have nickel tetracarbonyl here. But as I said, it's very toxic because it can easily undergo thermal decomposition. It can't withstand high temperature, or else it will be decomposed. Dia akan musnah, dan when that happens, dia akan membebaskan gas carbon monoxide. So this is not good to our health. Definitely, it's very lethal. It can poison. It can be reacting with our hemoglobin, and that will make some problem in our health. So that's the first method that we can use to synthesize our carbonyl complexes. Direct insertion of metal with carbonyl, but we have some restriction here that only iron and nickel can be directly reacted with our carbon monoxide. Unless we change the condition, then there will be a different story. Now, the second one will be reductive carbonylation. We have here from metal halide. I'm using chromium chloride here. So we have carbon monoxide, and we have aluminium. So in this case, our chromium stacking all carbon monoxide, forming chromium hexacarbonyl. So this is reductive carbonylation because there is some reduction and oxidation taking place here. We can also do reductive carbonylation from metal oxides. So rhenium oxide here, I2O7. So using carbon monoxide, so you're going to get the metal complex. So we can make carbonyl complexes through direct insertion and reductive carbonylation. Anyway, if you have questions, you can just post your questions on the chat box. Yeah. Maaf ya, last 2 years I can speak Indonesian language very well. Saya already. Sekarang sudah lupa, jadi susah sikit. Okay. Now next, we can have thermolysis of lower nuclearity carbonyls. So nuclearity is a term that we use to indicate how many metals that we can have in any given complex. So for example, we have here osmium here. This is mononuclear. We have only one metal, and this is trinuclear. We have 3 metals. So we can actually produce or synthesize new complex, higher nuclearity one from lower nuclearity carbonyls. So we use thermolysis. So thermal is used here, definitely Haber, and then lysis where we break it. So we have high nuclearity of complex. And last but not least, we can also synthesize carbonyl complexes using photochemical bond cleavage. So, meaning from iron, penta, now we have 9 carbonyl here. So, photochemical means we are using light here in the reaction. So, there are 4 ways to synthesize carbonyl complexes. I hope you are clear with that. Well, actually, the syllabus is quite extensive for organometallic chemistry, but I didn't take everything, and I'm not going to deliver everything here. I just pick few important parts which I think important for chemists. When you're graduating later, you might be dealing with various types of samples. You might be dealing with organic samples, organometallic samples. So it is important for students, graduating students, to understand how they are going to use their knowledge in spectroscopy, IR and MR, and how that knowledge can be used to identify or characterize various types of samples like organometallic or organic compounds. So that's why I chose experimental evidence for back donation. We understood earlier that there are 2 steps to be taken to form carbonyl complex. Kita boleh ada sigma donation from the ligand to metal, and the second step, which is the crucial part, is the pi back donation from metal to your ligand. So as I said earlier, we are actually taking electrons from our HOMO of carbonyl, and then we put the electrons into empty orbital of our metal. So that's the first step. This is sigma donation. Sigma donation means there is a sigma bond formed. And then the second one would be pi back donation. For pi back donation, since as I said earlier, metal is electropositive by nature. When at a certain point, your metal cannot be accepting too much electrons, because excessive electrons, abundance of electrons, will disturb the stability of the complex as a whole. So metal needs to be donating the electrons back to the ligand. So that's why we have pi back donation. So that's why sometimes you see just now we have metal with positive charge and sometimes metal with negative charge. It is negatively charged when they have excessive number of electrons, and they can cope they can reduce the number of electrons by giving back the electrons to the ligand. And then those electrons are going to be transferred into LUMO, which is pi antibonding. That's why we call it pi back donation. So this is actually the step that I have explained earlier, but I just want to re-explain, because later we are going to see how back donation can be seen through experimental evidence. Oh, by the way, there is a term here, correct symmetry here. Overlapping of orbital definitely needs to be happening when they are having the same symmetry, like this is happening at Z exits. So only then the overlapping of orbitals is likely to happen. So again, you will be hearing me talking the same thing, but this is the fundamental part of the lecture. We're going to talk about pi back donation. We're going to talk about sigma donation again and again, repeatedly, because this is what it is all about. And then we call it these synergic effects because it is important for the electrons to be donated from ligand to the metal, as much as it is important for the metal to be donating the electrons back to the ligand. So that's why we call it synergic effects. So pi promotes sigma. The pi back donation will promote sigma donation. So when you're giving back the electrons to the ligand, now ligand having extra electrons, so ligand will have the tendency to give back the electrons to your metal, and metal, on the other hand, will give back the electrons to the ligand. So the process is dynamic, I would say. So it will not stop. The moment electrons are there in the ligand, they are going to give back the electrons back to your metal, and vice versa. So that's why we call it synergic effects here. So sigma promotes pi, donation makes the metal more electron rich. When the metal is rich in electrons, they are negatively charged, slightly negative. This is not okay for metal, tak boleh jadi pada metal. So dia kena reduce sedikit the negative charge dengan mendermakan semula elektron to the ligand. I hope it is okay with you. Okay. Okay. Now, evidence from IR. IR is infrared spectroscopy. We're normally using FTIR. I'm sure all chemistry students are very, very familiar with IR. So the basic thing with IR is that we need to base our interpretation on Planck's equation. So this is the equation: E equals to H nu equals to Hc over lambda. This is common equation. H is Planck constant, and we have nu here, frequency, and then we have c, speed of light, and we have lambda. This is the wavelength. So in any given IR spectra, we should be seeing a frequency. So we can tell the strength of the bond based on the frequency. So, or rather, we call it stretching frequency. I'm going to elaborate further on the type of frequency that we can have on the IR. The important part of this particular part would be, I just want to tell that we can actually interpret the strength of the bond of our organometallic compounds based on the frequency of based on their frequencies. So let us focus on these four parts, four compounds. The first one is free carbonyl, meaning there is no metal. This is not a complex. This is just free ligand. This is unbonded, tidak terikat dengan mana-mana logam. So ini frekuensi untuk carbonyl. Frekuensinya adalah 2143. It's quite high. So carbonyl is a strong peak, very strong, intense peak on the spectrum. We could easily see. And then when we complex with manganese, it reduced to 2090. Kita complexkan lagi dengan chromium, reduce lagi jadi 2000. And we complex with vanadium, it reduced to 1859. So we can ignore this first. Yeah? We focus on the frequency of carbonyl. Now, from these frequencies, we can make a hypothesis that there must be something to do with the strength of the carbonyl that lead to these frequencies. So there is a reason why we can have these such frequencies, and to explain that in details, let us look at this table. Jangan panik ya, mungkin nampak sedikit dance di sini. This is quite do not get panic as yet. This is introduction, yeah. Because that's the reaction that I would normally get from my students as well. They would get panic as soon as they see this kind of table. But nothing fancy here. This is just basic chemistry, not even inorganic chemistry. We're going to talk about nuclear charge. So let us compare manganese, chromium, and also vanadium here. We have atomic number, different atomic number definitely, different atom, different atomic number, 25, 24, and 23. So they are arranged in decreasing order. So the nuclear charge will be that of atomic number, is 25 plus, 24 plus, and 23 plus. So nuclear charge is coming solely from the proton number. And number of electrons on the metal center. So for manganese, it is manganese plus. So meaning we have lost one electron. So that's why the number of electrons is no longer 25. It is 24 electrons. But for chromium, nothing happened. The number of protons stays. The nuclear charge stays. But for vanadium, it is negatively charged. Now it is 24 electrons. So meaning we have gained one extra electron here. Now we need to compare, kita perlu membandingkan di antara nuclear charge dan juga jumlah elektron, bilangan elektron. Jadi untuk manganese here, nuclear charge yang 25, elektron yang 24. So the nuclear charge is greater than the electrons. But for vanadium, you're going to ignore chromium for a while because there's nothing much interesting happening here. But for vanadium, the nuclear charge is 23, but the electron number is 24. So electron is more than the nuclear charge. So what does this tell us? Apa yang kita boleh dapat daripada maklumat ini? So definitely we're going to talk about the attraction between nucleus and also electron. In any general chemistry courses that you have taken, I presume, kita semua faham bahawa ada tarikan di antara nukleus dan juga elektron. Tarikan itu akan menjadi lebih kuat sekiranya nuclear charge is greater, nuclear charge lebih kuat. So dalam kes yang ini, dalam kes manganese, the nuclear charge is greater than electron. So that's why the electrons are being tightly held. Dia diikat dengan sangat kuat. Berbanding dengan vanadium, they are less tightly held. So this will affect the pi-back bonding because when it is tightly held, then definitely agak sukar untuk kita mendermakan elektron semula kepada karbonat. So there will be less likely for the pi-back bonding to happen. And then consequently, dan kesannya sudah pasti LUMO kita yang kosong tadi tidak akan terisi atau kurang terisi. So electron density of LUMO will be lower. Yeah, look at this first column. So lower LUMO of carbon monoxide, and then the bond order will be higher, the strength will be higher. When there is less pi-back bonding, the bond strength will be higher. And from the IR frequency, we can tell that the pi-back bonding is low bila frekuensinya tinggi. So frekuensinya tinggi bermaksud strength carbonyl itu sangat tinggi. So we need higher frequency because frequency and energy is directly proportional, berkaitan langsung ya. Jadi sekiranya tinggi frekuensi pada IR, maksudnya tinggi juga tenaga yang diperlukan to vibrate the functional group. So that's why when nuclear charge is higher, the pi-back bonding is lower, and now the bond is stronger. As opposed for vanadium, so it is less tightly held, so degree of pi-back bonding will be higher. And the bond order and the bond strength will be lower or weaker. So we can see from lower frequency. So that's why I would like to reverse back to here. That's why when we compare all these frequencies, vanadium has the lowest frequency because it has the weakest bond. So definitely free carbonyl is the highest frequency. Look at this manganese, this is the highest frequency because it does have the strongest bond. Okay. That would be that on the principle, and then as well as on formation of carbonyl complexes, as well as on the IR evidence. I would like to reiterate again that for any complexes, actually the same steps will be taken. About the same step will be taken. That you need to have electron donation from your ligand. That's why ligand is called ligand anyway, because ligand perlu ada electrons untuk didermakan, or else tidak akan ada sebarang interaction between logam dan juga ligand. Jadi ligand itself must be able to donate electrons to the metal. This is the first step, and this applies to almost all formation of complexes. And second would be the pi back donation. This is the interesting part of coordination chemistry, where the metal, since it is electropositive by nature, is not being able to hold that much of electrons. So by hook or by crook, it needs to be giving back the electrons to the metal. I'm sorry, to the carbonyl. So the things that we learn here is actually the IR fertilization. When we have organometallic compounds, the first thing that we want to see is to compare between ligand and also the complex. They must be shifting on the IR spectra. If there is no shifting at all, or the shifting is too low, like the delta frequency 1 or 2, it is quite difficult for us to claim that the complex tu dah terhasil dengan berjaya. So it is not okay. So IR is the good way for us to tell. Oh, so the complex now okay. The complex has been successfully synthesized by looking at the shifting. The shifting is actually tell you whether the bond is weakened or the bond is strengthened. Yeah, so it can be. That's why there is no strict formula that says it should be higher frequency in complex or lower frequency in complex. It can be either way, because your bond can be weakened or strengthened. It depends on the type of ligand as well. But that's another part of inorganic chemistry. But so yeah, so that's all on the IR evidence. That's how you interpret the strength of your carbonyl based on the frequencies, and that should be your justification or judgment should be based on the Planck constant or the Planck equation. Now applications, well, there are many applications of organometallic compound. You can just, when you type the organometallic application in medicine, in pharmaceutical industry, as catalysis, there are a plethora of applications of organometallic compounds. So I just want to summarize a few interesting part of organometallic compound. So this is Wilkinson catalyst. I would say the most popular catalyst in organometallic catalysis. We have rhodium here and PH3, and this is phosphine. Now again, even though now you might be asking, this is we don't see any metal to carbon bond, but this is still considered as organometallic compound. As I said in the research article, when you search, the definition will be very broad. It doesn't confine to M2C bond only, but this is just for the sake of the syllabus. So the catalyst is widely used. As I said in the introduction, that we can have hydrogenation using palladium. Palladium, nickel are the most common ones, gold, and so on and so forth. So we can use those metals complex with various types of ligands, and can be applied in hydrogenation, for example, in polymerization, and also carbon-carbon coupling reaction. There are many types of carbon coupling reaction. This is what our research lab is doing, has been doing for years. We are more interested in looking at the catalytic activity of our complexes in carbon-carbon coupling reaction. I'm not sure how familiar we are with the reactions, but some of them are quite popular. For example, Hack and Suzuki. Hack and Suzuki received their Nobel Prize in 2010, and then we have Sonoga-Ashira coupling reaction. That was the reaction that I worked on for my PhD. That is to produce alkyne. So I would say mostly for organometallic compounds, they are widely used as catalysts in many types of chemical reactions. And the second part would be medicines and pharmaceutical. If you noticed earlier, I have talked about cisplatin and oxaliplatin. These are the common examples of organometallic. Even though there is no metal to carbon bond in cisplatin, for example, I don't have the figure, the structure here, but of course, it's just platinum and chlorine and ammonia in your cisplatin. But again, it is still considered as organometallic compounds. So it works very effectively against various types of cancer. So our organometallic compounds do have anti-cancer activities on not only on the cells. Certain compounds in fact have gone clinical trials, sudah dipasarkan pun sebagai ubat, and most of the chemotherapeutic drugs, now you can see ada yang guna oxaliplatin, carboplatin, as well as cisplatin still. Yeah? But of course, there is side effects of these drugs. But this is the thing that we at UITM also would like to explore. Of course, it will take maybe 10 or 20 years in time. But we are moving towards that. We want to find a better alternative to these platinum groups. So we are exploring palladium, nickel, and these days we would like to venture on lanthanides as well, on the F block element. And then we have anti-malarial agents and antibacterial agents. This is ferrocene. Ferrocene, we have iron, and this is the ligand. This is the common ligand in our organometallic compounds. This is cyclopentadienyl. So 2 cyclopentadienyl, and iron is being sandwiched here, terletak di tengah-tengah di antara dua cyclopentadienyl. So the structure can be changed easily. When the structure change, the color also change. If you understand, the color here is orange, ferrocene. And we have ferroquine. So ferroquine is used as anti-malarial. So this is the structure. We have the basic structure of ferrocene here, and attached with some other ligands. So far I have covered all from the principle, the basic principle. I'm sorry if I went too technical, because that's the subject all about. And the second part on the formation of chemical complexes and how do we characterize our organometallic compounds. And last but not least, on the applications. And be a bit more on, I actually created a YouTube channel. This is called DSF&A. I've never had one, not until UITM or Malaysia announced PKP, Perintah Kawalan Pergerakan, and all lecturers are asked to conduct online classes. So I find this is the best way of having it, by having a YouTube channel. So some of my explanations might not be that clear to you. Mungkin tidak begitu jelas. Saya punya penjelasan sebentar tadi, kalau tidak begitu jelas, mungkin boleh lihat ada beberapa video di YouTube. Ya. Jadi itu saja, saya buka untuk sebarang soalan. Terima kasih. Okay. I've never had any experience synthesizing carbonyl complexes in the lab. If I said earlier, there are many ways of synthesizing our compounds. Kalau dilihat yang tadi, kita ada beberapa cara. Yang first tu only applicable for iron and nickel. So if you want to make sure whether it works best in the lab or not, so we have to know the type of metal that we have. I've never had any experience producing carbonyl complexes in the lab, But I would say definitely carbon monoxide is quite dangerous. If you have this, it must be conducted in a confined area. So yeah, because we need to have a special chamber for to carry out this kind of reaction. So normally we have a passing tube where we direct insert our gas into the reacting flask. Yeah. Why the wavelength of why the wavelength opposite? It's not really opposite because what does it mean? The wavelength of CO bond opposite to the wavelength of MC bond. Oh yeah, of course. Okay. So the frequency, it's not the wavelength, it's the frequency of the CO bond is totally opposite to the frequency of metal to carbon bond because um, the metal is directly bonded to your carbon and carbon is directly bonded to your oxygen. So it's just um, when CO bond is strengthened, the MC bond is weakened. So sekiranya bond CO itu semakin kuat, maka bond metal dan carbon akan semakin lemah. Sebab itu frekuensinya akan jadi opposite. So for example, this one, we agree earlier, tidak bersetuju bahawa this is the lowest frequency among these three kerana dia mempunyai bond yang paling lemah. Jadi ini ikatan yang paling lemah, tetapi MC bondnya akan kuat because kita ada donation from carbon to metal and we have pi back donation from metal to carbon. So sekiranya CO itu lemah kerana bondnya semakin kuat, kerana banyak pi back donation, maka MC bond itu akan semakin kuat. So that's the relationship between CO and MC bond. I hope it is clear. Okay. Okay. Ya, silakan. Oh, by the way, we forgot to record this list. Oh, okay. Okay, we got a question here. Wah, dia panggil saya Prof Nizam. Alhamdulillah, amin. Awal lagi jadi Prof ni. Amin. Agree from chemistry department. Okay. Uh, Yeah. That's why other than cisplatin, I also talk about the application of ferrocene here. So, like for this rhodium complex, it does not have any metal to carbon bond, but it is still organometallic compound. As I said earlier, it is a broader definition of organometallic compound. The definition that I gave earlier only applies for the subject, but we can still consider this as organometallic compound. But for medicines and pharmaceutical application, for medicinal and pharmaceutical application, I did mention about ferrocene. So this ferrocene definitely has a direct metal to carbon bond. You can see this metal and it is directly bonded to your carbon. This metal also has a direct bond to to this metal. So yeah, so it does have metal to carbon bond for ferrocene. And anything else? Well, maybe I can drop my email letter if you want to. Atau mau sambung S2 di UiTM juga bisa. Yeah. Okay. I think some of my students might be having class now. They have to go. Oh yeah. Oh, okay. Yeah, electronegativity is greater than C, but why is it that the metal is bound by the element C? So, because from the good question anyway. Um, yeah, all electrons in the carbon involved in the formation of molecular orbital, but not all involved. Not all electrons from oxygen involved here. And when we see the structure here, well, even though oxygen is more electronegative, but carbon will have the ability to donate the electrons. Well, when I say it is from carbon, it is actually from the carbon monoxide, because it's like this. Because it's always a molecular orbital that we are talking about. It is not, when they are forming a molecule, it's no longer individual atomic orbital. So the molecular orbital that we have constructed here actually belongs to um, carbon and also oxygen. It is a mixture of both. So when it is from here, well, actually, technically, we can say that, oh, this is from oxygen, this is from carbon. When it is atomic orbital, yes, we can. But once we construct molecular orbitals, it is now overlapping already. So one orbital can have one electron from carbon and one electron from oxygen, right? So for the sake of illustration, so saying that you must take electrons here from orbitals on the carbon on of our carbon monoxide. Good question anyway. I've never received the kind of question from my students, but I hope they learned something new today. Oh yeah. Thank you, Pak Tige.
Cukup Pak, sudah.
Terima kasih.
Thank you, Pintas Nizam.
Yeah. Oh, okay. Yeah. Yeah, probably. Okay. Thank you very much for having me as kerjasama ini berterusan, insyaAllah. Ya, insyaAllah. Ini sekali. Okay.
Alhamdulillah. Terima kasih Pak Siti, Pak Nizam.
Terima kasih ya semuanya. Terima kasih.